Welcome to the course Algorithmic Design. So this one works only from the top. You can just go under top and that's it. Okay, so what is happening here? There are some randomly distributed charges in this grid, and they basically make these circles bigger or smaller. So the radius is dependent on how far away we are from these sort of attractors. And basically, the influence of all the attractors is added up, but it's scaled according to the distance to the attractor. So if I'm point like here, this point is basically measuring the influence from, this charge here, this one, and basically all of them that are in the field. But because they're very far away, the cumulative influence is actually rather low. And of course, here we have a case where the point here, for example, or in the center here, it is closest to this charge, or the charge is, I guess, somewhere here in the middle. So it has kind of, some maximum radius that it can have. We cap this radius, so the radius cannot become too big, and it's also it's also kind of feeling the influence from all the other charges, but again, they are very far, so so there's it cannot they're not really influencing it that much. But there are some points that are maybe in between, maybe this one here, which kind of feels the influence, from points that are kind of closer to it. Okay, and that's basically how these metaballs are created. Also, again, the theory reference today is the here metaballs. So again, they're very popular in computer graphics because, again, you can sort of use them to quickly simulate like blobs or fluids. So again, this is not really fluid dynamics. So we're not really simulating fluids, but if you're a little bit smart how you do it, you can simulate, you kind of make things look a little bit fluid-like, so blobby-like. And I guess in the 90s, they were very popular. That's why when you kind of Google this sort of a blob architecture, these are basically metaballs. Okay. So yeah, used in computer graphics and based on the formula for calculating the electric field. That's it. You can also have kind of negative metaballs, which are sort of the negative influence, let's say. And then, yeah, I guess they're used in design a lot to get this kind of a blobby feel for things. Okay, maybe let's put which one. This one is nice. Okay, so this we basically do exactly this here, but in 2D. And I'll just try to explain a little bit kind of what's happening. So we have a separate function here. This function is just calculating a random 2D point. Okay, basically, if you give me a maximum x and maximum y, this function, if I run it on the bottom, let's run somewhere here, it will give me a random point inside these bounds for maximum x and maximum y. And we do this because then we can sort of have this code here, we can sort of collapse it, and we can use this function inside the code here. Or so we get this attractor, which is then basically a random point. Okay, so at the beginning, this function is just defined. Yeah, this enable redraw to false. We kind of purge the layer, cleans up the default layer. And then we define our variables, or we have the cell number. So how many, just a minute, where do we use cell numbers? That's this number here. That's basically, yeah, that is the grid size. Or so there's the grid size, which is sort of the size of this square in Rhino units, but there's cell number, so how many of these points are there, how many cells are there, and then the size of the cells. Or so this distance here is 10, or so this is, I think, 10. From here to here is more or less 10. And then grid size is basically the cell number multiplied by cell size. Then this is charge. This is like the this is sort of the influence, I think, so how strong the charges are. If I reduce this, for example, by 10, if I run it, you will see that now you will get a bit different effect. Yeah, so these are the charges, or they're kind of, these are the points, and the charges, they're now smaller. So their influence is smaller, or so they kind of, they're just more like points, like point charges. and I can kind of increase them. Maybe I can even go double from what they had before. So this means the charge is just very strong. So it kind of tends to kind of envelop more of the field. Also, I can change the kind of the influence of these charges. Here I call it charge because it's, again, the formula to use is basically formula for electric charge. So it's kind of just useful to use the same term. Okay, and here we have a tracker number. So how many of these random points will be distributed? So if I put 10, there's just going to be 10 points, and I can just have kind of 2 points also. So they're just going to be somewhere. Okay, 2, and let's see actually if I increase the charge. Okay, maybe it's easier to see if you have only two of them. Also, there are kind of some charges. They kind of float around, and sometimes they will come close to each other, and there's going to be sort of cumulative influence. Okay. Okay, so let's see actually how the code works. Okay, so if I go inside, creating random attractor points. So first, I need a list of attractors, which are just going to be points. So I use this function called random to the point to basically create these these random points that will be just distributed along this kind of square grid. So if I have attractor number, if I have 4, there's going to be 4 of these points, and they will be added to this attractors list. Okay, and then it's actually very short. Okay, and then I have the main loop, drawing circles. So basically, I will draw this. Underlying grid, which is like a sampling grid, and the closer I am to a charge, the bigger the radius are. So here, first I create a point, which is at coordinates, I, j, multiplied by cell size. So it's just going to scale to whatever the grid is. And then first I will say the radius will be 0. And then I will go through all the attractors, and I will calculate the distance to these attractors. So there's here rs.distance, so distance between attractor point and the point. So again, point is maybe here, and then the distance would be from here to whatever the point is, somewhere here. That's one distance. Second distance. So yeah, so again, the attractors, they stay at the same place, but as I'm going from point to point, these distances will of course change. Okay, so this point here has one distance, second, third, fourth distance. So that's calculated here, and then I'm adding it. So I'm kind of calculating the radius by basically saying there's a charge, that's some absolute number, divided through square of the distance. Okay, and basically this radius is somehow like I'm basically adding the influence, like the radius influence for different charges. So that's why in this small loop I have like plus equals. So the radius, it will become just bigger for every charge. And of course, if I'm closer to the charge, it'll just be bigger. Now I just want to show you what happens if I don't have this other condition here. So if I remove this, so this condition here is just kind of preventing the radius from becoming too big. And I just want to show you what happens if I don't have it in. Okay, so it's clear that if I don't have this cap here, maybe I can reduce this charge to something smaller. The radius can become very big because some points are like very, very close to the, some points are very, very close to the charge. And then this distance is very small, squared becomes even smaller. And if I divide some number with a very, very small number, I will get a very big number. So I'm kind of adding a very big number. That's why some of these, they become like super, super big. Or just do it again. Okay, so some of these charges are just, some of these radii are just huge. So go back to what I had before, maybe like this. So what I want to do, I want to say basically, well, yeah, what I want to do is basically say that Yes, some are super huge. I want to say that if the radius is bigger than the cell size, or or half the cell size, then I will just snap it to this cell size. Or so I don't want the radius to be too big. I don't want it actually to go beyond what the size of the cell is. So that's why I have this conditional here. This conditional is basically just checking if the radius is bigger than half of the cell size, then I can write also like this: radius equals half the cell size. Or so if it's bigger than some threshold, I will snap it to the threshold. I'll just define it to be basically that threshold. That's a little bit similar to what we did, I think, last week. We did exactly the same thing with the sizes of the vectors. When the vectors will become too big, we would just snap them to maximum size that we define, and here we just define it like this. So I can change this. I can maybe say, well, it's actually going to be the cell size. Why not? So now some of these that are in the middle, they will kind of be double the cell size, so they kind of overlap in this way. So that's kind of one way of doing it, but it's a bit maybe convenient to half the cell size, because then when I add this, and then yeah, in the end, I'm just adding a circle. There's a point, that's the center, and then the radius is, well, it can go again maximum the half the cell size, which will make the circle basically as big as the cell. Oh, they changed. Okay, they're here. So the biggest circles are actually the size of the cell. So they kind of touch perfectly. Or so these ones are all the same. They have the same radius because they're just, yeah. And this is in a way, in physics, this is called, I think this is called like field renormalization or something like that. And to some extent, it has to also be done when you calculate, for example, electric charge. Yeah, because if you would in theory have, yeah, well, but you have kind of quantum discretization, so you cannot really have two objects at the same place, so you don't really have that kind of issue. But to some point, to avoid these singularities, the renormalization needs to happen. And here, of course, it's convenient because it makes these blobs just a bit, makes these blobs kind of manageable. Okay, I just realized that I have 2 minutes left for the lecture, so I will try to finish by, there's another version of this same code, which says attractor field outlines, and there we just add one single line. Where is it? This is all the same. Yeah, we just added, or I just added this line here. I think that's the only, yeah, that's probably the only change. Actually, 2 lines. We define something called a thickness. And then we have another conditional here. We say, well, if the radius is smaller than some number, and if it's bigger than some other number, then we add the circle. Otherwise, we don't do it. So when I run this, I basically get these, I get these outlines. Also, if the radius, but basically that means this kind of charge. Or so if the radius is, the circle is bigger than, what did I put here? If it's bigger than, yeah, kind of cell size multiplied by thickness divided through 2. So that's this area here, I think. I'm not actually sure if it's bigger. Yeah, then I'm allowed to draw a circle, or if it's smaller than this, then I'm also allowed to draw a circle. Or so basically, these in-between areas are being, so this where the circles are very small and where the circles are very big, these get left out, or so there are no circles there. So I get this kind of a band in between, and I can change now this thickness, for example, to maybe 0.2. Let's see what happens. I think I should get a thinner. Oh no, actually here, yeah, here the threshold is a bit changed. Thickness. Okay, so here I kind of left out these areas in the middle. Also, there's kind of a gaps. Okay, kind of some caves that happen. And if I increase this number to, for example, 0.9, you will see what should happen. I think I should get much thinner lines. Yeah, I get this kind of thin lines, like 0.8. I'm trying to get these kind of outlines, or and again, because we work with this in this grid fashion, this like a pixelated outline, or so it's not really something that's not even closed. Maybe increase the cell number to 200. Let's see what happens. So I get a bit higher resolution if I do this. Okay, and then maybe charge, we double it, something like that. Okay, so you can now play with this sort of a band. Yeah, we get a bit kind of maybe nicer results. Actually, let me change it even more. So now I kind of increase the grid, increase the charge. So I get kind of a higher resolution. So these bands are more, and they look maybe like something like this. They're kind of more smoother because I have a bit more room to play around with. Okay, maybe actually 85 would be better. Okay, so again, a very slight modification to the previous script enables me to extract these areas where technically kind of the charge is similar. So these, like what's common with circles in these bands is that they have a very similar radius or radii. So in a way, if this would be an electric field, this would be the areas with a similar charge, or. And these are also called, depending on which papers you read, these are sometimes called. Functional surfaces, or so it's a surface that is defined in a way as a function. Yeah, maybe functional surfaces, I think. So there's this kind of B-reps, boundary representation of surfaces, and there are these kind of F-reps, like functional representation of surfaces, which are so the metaballs are example of those. Okay, and then again, this is just like graphics, but you can imagine that if you now start just extending the script a little bit, you can start kind of, because this is flat, but you can basically start extending this into 3D, start fixing the seed maybe, and kind of moving these charges around, and you can start getting kind of shapes that go maybe go into height. So you can use this basically as a kind of a building block to create three-dimensional geometry. And we will not really do this because that's kind of really now kind of, well, we might do it one or two examples in the future, but I would really like to show you kind of the width of what's possible. And then extensions, you can sort of think of them as these mini projects that you do. Or so you can kind of think of, if I take this, just code, it's like barely 50 lines. How can I kind of extend this into sort of a mini project if I imagine this is going to be maybe floor plans of a building, and these blobs are some kind of spaces, and when they come close, suddenly there's a connection that happens between them. So you can kind of start extending this into a more spatial story. That's how I would like to approach these mini projects.